Okay, while you're filling up your feedback forms, I'll just take some topics to introduce you with some new upcoming domain, and especially with regards to the GIAN. So what are we talking about? How the society is impacted in terms of ethics and in terms of fairness. I'll give you a case study, and then I'll open up some other topics that might be interesting for your future work. Okay, before I get in there, I just wanted to tell you that it's a joint work that was done with the student, the PhD student on the top. She just graduated recently, and then our postdoc at that time was professor in Taiwan, and our colleague here. And the article is freely made available. And the idea here is that we wanted to study the implications of deepfake detection in terms of deepfake, in terms of biases and ethical considerations. I'll take this as an example, but you can apply this for many other use cases, right? I'll tell you that where other, which other avenues are when you are from this. Okay, so let's start with the aspects of ethics, right? So first, in the last 2 days, I've been showing you this graph over and again to tell that once I have the deepfake, then I can attack the biometrics. So that means I have established that we need to have attack detection mechanism. Now we know that we can create a lot of attack detection mechanisms, but then these attack detection mechanisms have to be fair. Fair in the sense it should not be rejecting always people from, let's say, from Jabalpur versus people from Indore, right? We want to treat everybody equally, and to achieve that, we want to achieve systems that are fair and bias-free. So I'll tell you what is bias in a short time, but let's just talk a bit about the concerns, right? Why are we talking about these things? So deepfakes are typically very problematic for offenders, right? Maybe if somebody makes a picture of me, puts it online for fun, it's probably okay. But when we take the females, then it's more problematic, right? So we kind of understand that if you use the videos, if you use the images for creating the videos of for adult content or pornographic content, it's really damaging. Right? It has a very large impact on the society. It has a large impact on the people who are impacted. So we need to have this kind of mechanisms to detect them. So that we are very sure. Now here, if you see the news clip that I took from one of the websites, it says that 8 out of the 10 pornography websites, they post deepfakes, which is quite alarming. Right? And then there are approximately this 9% of dedicated deepfake pornography websites who are only providing the content based on that one. The problem here is that it's not just about this content that is being created, fabricated, which is using deepfake. But it's a bit of a problematic thing because we do not know which images are, right? And whose images are being used to get these kind of samples. So we need to be very considerate to such kind of factors. And then we have the second problem. One is the gender. We have established that gender is a problem. And the second thing is the race itself, right? When I talk about the race, I'm talking about broadly in terms of ethnicity. So if I have some kind of systems which are either face recognition system or deep fake detection systems, any of these deep learning based systems, we should always make sure that they do not negatively impact the people. And again, I took a video newspaper clipping back from 2021. There is a problem for marginalized communities. When we say marginalized communities, it could be any community that is not in the training set. Right? It could be somebody that is underrepresented. So let's say, for instance, if I'm going to create a database of all the people from India, and then I only focus on people from Delhi, it doesn't represent the whole of the country, right? So then I have smaller group which kind of overrepresented, and I have a group that is overrepresented, and then I have small subgroups which are underrepresented. So the moment I have this, then it can be that if I train a system in Delhi, and then for everybody that is coming from, let's say for the sake of other example, let's say Kashmir, then it might be rejecting all the people from Kashmir as deep fakes, which is an unfortunate situation, right? So one thing is the gender aspect, the second thing is the ethnicity aspect. And this is a common problem, right? And then you can also kind of you can kind of extrapolate this problem for medical imaging. Now, if I have medical imaging data sets in a similar setting, I might be having a large representation of female from a certain region, and their eating habits are different, their living lifestyle is very different. And then if I'm trying to use that systems on another population, let's say population from South India, their eating habits are different, their lifestyle is different, so it might not be performing very well. Right? So this representation of data set is a critical factor, in both in terms of gender and in terms of ethnicity. So if you look at the definitions of this bias, the bias is in the Oxford Dictionary is written as a strong feeling in favor or against one group of people. So it's not just saying the favoring part, right? It's also saying you are discriminating against another group of people. Or it's typically in a one-sided argument. But now, if you go to the same definition in the Cambridge Dictionary, it also says very similar. It says supporting or opposing a particular person. So I might be very biased to Susanta. I might not be biased to somebody else, right? So it could be also, I could be very opposing to Susanta. Whatever he comes up with an idea, I say, oh, this is not a good idea, right? You get the ideas of this bias that can be said. Now, if you look at the bias itself, there is a very wide definition of bias. So this comes from the field of psychology, so I'm really not an expert in psychology. But if you read the books, they categorize the bias in different taxonomy. And what we will be talking about today is that we'll be talking about this data set bias, under which we will talk. It's more question. Better? Okay. Okay, so now we can talk about data set bias, and then we can talk a bit about algorithmic bias, machine level bias, and then we can talk about decision level bias. So let's start one thing at a time. What do we mean by the sample bias and the exclusion bias? So in the sample bias, we are talking about maybe my data set is completely focusing on one group of people, and I'm not considering all group of people, right? And then I have the second one, exclusion bias. So then I kind of inherently design my data sets in a way that I do not take into account some people, right? By choice. This is also some condition. And then you have algorithm bias, which means that your algorithm is there has been shown multiple times in the face recognition community that people from certain skin color were discriminated all the time. And this has even led to some cases in the court, especially in the US, where some people have been arrested just because they had a darker skin color. And in the crime scene, they could only spot one person who had a dark skin color, and then it was established later on that that was not the person that was existing in that scene at all. You have got that thing. And there has been this other media cases, if you have followed it, where there have been number of cases that have been raised against the state, where their false implications have been questioned. And in the worst case, you can also see that this kind of algorithmic bias can lead to the a bigger impact of a person's life. It can be completely destroyed, which is very unfortunate. And then you also have this anchoring bias, which I'll talk about in a short while. And then you have this prejudice, which means we always assume that we have some kind of bias inherently, right? So I have a decision telling that, okay, maybe let's assume people from MP are extremely smart. And this is a bias that I have, that I've been brought up in that culture, and I have this from my childhood, and it's inherently in me, right? And then I also have this measurement bias where I'm trying to measure, maybe I'm skewed. I'm always preferring one over the other. And then I have the confirmation bias. So confirmation bias, again, is a very wide topic or a big topic by itself. I'm not very qualified to talk about that. But if I can just summarize this very shortly, it's something that I have a bias and then I confirm it, right? So I come up with a bias telling that, okay, I've been growing up in my childhood telling that people from MP are extremely smart. I come here, I meet all of you, then it kind of enforced to me that you're all smart. So that kind of is a confirmation bias. Okay? So you'll not be able to discuss all of these things, but why should the scientific community worry about this? So if you look at the old data sets that we were talking about, we are thinking about this collection and then database collection itself, and then the manipulation part and the detection part. So here there is a lot of things that can come into picture, right? So what is the collection mechanism? I'm going to collect the databases that are available from the internet. And who are these people? Typically celebrities. So if I'm just taking the images of celebrities, I'm not considering the entire population. And this was the initial case in the deepfake detection, right? So now you can also extrapolate it, face recognition, you can extrapolate it to other kind of data sets. So if you look at this, if you want to really study how the system is performing, if you want to tell that if my deepfake detection method is fair for all the population, you want to have all people represented in the data set. To start with that, to start for that particular analysis, what do you need? You need to have the annotations of all the people, right? You need to have their gender information, you need to have their ethnicity information, you need to have their age group, you need to have which region they come from, and of course, you can keep on adding the other factors. What is their educational background? What is their social background, and so on. Okay, so most of the databases that we have as of today, they do not have this full annotation because they are scraped from the internet, right? That is the first problem. And then if I'm able to establish that it's performing good for male and bad for female, then I can make the gender annotations, and then I can measure the performance for male, and then I can see how much it deteriorates or improves for female. So I can do this relative performance analysis. And then on top of all this thing, there is a problem in the metrics itself. So the equilibrium that we are talking about today, it doesn't consider gender, it doesn't consider age, it doesn't consider social background. All it does is it gives a collective error rate which tells that, okay, the system is 97% accurate or 96% accurate, right? So there are a number of problems here. So even to establish this bias, we need to first solve those problems. And let's start taking a look at this simple systems first, right? So I thought let's talk about this sample and exclusion bias, and then I'll go to the second part. In the sample and the exclusion bias, we have this missing annotation problem, and then we need to solve this. And even before we started this work, the idea here was that we wanted to check where are we standing in terms of this defect detection. So if you look at the data set, so the number of frames that were available in this particular data set, which is UADFV, is approximately 49 people. And with 49 people, we had huge number of frames. The frames were around 10 to the power of 4, which is 10,000 frames. So by definition, the data set is large. But how many people are there in the dataset? It's only 49, right? So I can't really go and tell it that, okay, the system is performing with 97% accuracy when I have only 49 people. So 97% of 49 is approximately 45 people. So it works for 45 people and it pays for 4 people, which is not a bad scenario. But then if you scale it up for larger population, then it becomes much, much smaller, right? What should be the optimal frames What should be the optimal frames is a tricky question. So what you should consider is not the number of frames itself, but the representation part. Do you have all diverse conditions in your data set? So you can even work with, let's say, 30 frames per subject, but you need to have multiple subjects, multiple representations of multiple groups of people, gender, age group, ethnicity, and so on. So that is much more valuable. But generally, there is no general thumb rule as such. It depends on how you are training your system. I've seen systems that are trained with single frame, but I've also seen the system trained with multiple frames. So as you can see here, if you look at the last one, right, DFDC, which is defect detection competition, in that one they have 960 people, and total number of frames are 1 million plus, or 10 million actually. 10 million frames are available. So it depends on your use case. It depends on the algorithm that you're working on. Okay. So as you can see here, the generations, the first generation, the number of frames were kind of limited. The videos were approximately 1,000. And then if you go to the third generation, the second generation, it's slightly increased here. And in the third generation, you can see that it exponentially increased, the number of frames. And in terms of also number of videos, and in terms of number of identities. So what did we want to do? First, we wanted to. Okay, so the first thing we wanted to do was to find out, do we have equal representation of all the people? And then that would mean that somebody has to sit down and then annotate every single thing, right? Now there comes the first problem. If I ask you the first person and I tell you that, okay, can you identify which kind of ethnicity it is? Most of you might be able to tell me that, okay, it's an Indian, right? Now, if I take the same image and then give it to somebody in US who's not used to Indian ethnicity, they might put it as Asian ethnicity, right? So when they talk about Asian ethnicity, the whole of subcontinent of India, right? So it could be for a person from Europe or from US. This person could be anywhere from India, Sri Lanka, Nepal, Thailand, and so on, right? So now the definition of ethnicity also varies from the way that they're being taught or the way they are being exposed to. And then the second one, let's take the second example. And I've asked you, some of you people, that is that girl young? So most of you might say young, but for those people that are coming from that particular ethnicity, they would say that, okay, this person is not maybe young, is middle-aged. And the same applies to the first one, right? So we have known this person from our childhood. So we'll be able to tell he's not a young person anymore, he's a middle-aged person. But we can tell that because we have been exposed to that particular person over a long period of time. So what we wanted to do in this first case was to annotate the database. And this annotation was based on 7 different demographic attributes, which was typically, is it male, female, young, middle-aged, or senior? And then is it an Asian, white, black, and so on. Right? So then comes the second one, which is non-demographic attributes, which are typically the skin. The skin is considered as a non-demographic attribute because somebody from US can also be dark skinned. Somebody from Asia can also be fair skinned, right? So it is typically non-demographic attribute. And then you have the hair color, which can be black for multiple population, it can be blonde for multiple population. And then you have the other things such as beard, face geometry. Is it a square face? Is it a round face, oval face, and so on? And then the mouth again is how it can be common across different ethnicities. So that's the reason why it's classified as non-demographic. And accessories. So the accessories are nothing but your lipstick, your earrings, or your hairstyle, and so on. So the very first thing what we had to do there was to take the whole data set, multiple amount of data set, and then we had to annotate each of them. By annotation, what we mean is that if the particular ethnicity, particular attribute is present, we attribute it as 1. If the attribute is not present, we put it as -1. And sometimes it can be unknown, right? It's a machine. So it's a machine which is making decision and it cannot come to a conclusion. So then we kind of annotated the whole of the data set. And here the idea again was, how do I know that if the machine is telling that the first person is Asian? I need to also verify that, right? So to verify that, we made use of another work, which was from the postdoc that was part of this work as well. And what they did was they introduced 3 observers, and the 3 observers had to vote. So every frame they annotated, they said, okay, the machine is telling this is an Asian. What do you 3 think? And if 2 of them said yes, this is Asian, and then it was annotated as correct annotation. If it said no, then it was no annotation. And if there was no consensus between the machine and the human, then it was set to 0. Okay. So by doing this, we could create a huge annotation of all the data set. And here you can see that all these features are very imbalanced. And now, suddenly it jumps. So by doing this annotation, again, here is the way the annotation was done. So they took a source database which had all the annotations manually annotated, and then they trained a model. And from that model, every new database was sent through that annotation pipeline, and it would give a target label, and this target label was verified by 3 human observers. Right? So this is a huge process, very manual process, but somebody has to do it. Right? So the first work they did this, and they came up with all this annotation. And now for this particular person, it says very clearly that it's male, is white in skin color, the black is 0 because black is -1 because the skin color is not dark. And then is he bald? No, it is -1. And wavy hair, it's 0 because it could not come to a conclusion if the hair was wavy or if it was straight. And then there is also some controversial annotations. For instance, attractive. The machine classified it as 0. Now, for most of the young women, if you ask in India if this person is attractive, they probably would say yes, right? So again, there is a bias with the way we look at people. Okay. So there is also this other aspects. For instance, wearing lipstick is negative. And then there is also smiling is negative for this particular frame. So which means that we can now establish the performance of each of these factors with the defect detection. Okay. So what does this lead us to? It leads us to understand the data sets before we study the bias factors, before we study the ethical impact. And we see that if I have to study this, if the algorithm is good for young people, it's very bad because I see the labels for the young people are almost 0. Right? So if I take this particular celebrity 590 video data sets from YouTube, then it doesn't really have younger population. So I cannot use this for training an algorithm. And then if you look at the other aspects, you can also see that, okay, the data set has a huge representation of wearing glasses. Where is that? Eyeglasses. You see it is only less than some percent. And then many people are not wearing the eyeglass, right? So if I have to tell that the algorithm is performing very well for people wearing glasses and not wearing glasses, then this data set is not the right. Now, why would that be interesting for us? Because most of us are wearing sunglasses or whatever the glasses for reading glasses. And if I'm just classifying somebody as a fake because somebody is wearing a glasses, then it's not a good system, right? But then it's biased system. So we take all these different aspects and then we start analyzing them. When we start analyzing them, we see that some data sets are good, some data sets are bad. Now, if you go from that particular previous data set, YouTube data set, to DFT, the very first data set, again, you see this is kind of okay because the male and the female population is very well represented, but female population is not well represented. So this data set now fails in other criteria. And then you also have the other aspects, right? For instance, if you want to study if the person has hair or not hair, if the person is bald, then this probably is not the right data set to study the impact of this bias. So by doing that, we could now again, if you take one more example in the case of phase forensic plus plus, you also see a very similar trend. Now many of the attributes are active in this case. There are not many missing attributes in this case, right? So it kind of tells us, okay, this probably is a better data set compared to the previous two data sets. So if I want to go back and sell my system, I would also want to take this data set and then try to understand what is the performance on all these different aspects. Okay, and then there is the next version that came that did not consider these aspects. In the next version of deeper forensics 1.1, the number of attributes that we had defined is extremely skewed here. Although the number of frames are 12.6 million and 50,000 videos were available, it was very underrepresented. But the good thing is now it has male and female somehow better represented, but then all the other factors are low. What does this mean? So this means now we have a publicly available dataset. It's made publicly available. If you just go to that link, you can download it. And this has the annotations for approximately 65.3 million annotations on 41 different attributes. The 24 plus 7, 34 plus 7 attributes, and all these 5 datasets. So you have CelebDF, you have deepfake detection, phase forensics plus plus, DFDC, all of them are being annotated. And if you are creating a new dataset, you could also use the same mechanism to annotate your own datasets. Okay, so what did we end up with? As compared to the previous datasets, now we have massive and diverse annotations. This enables us to study all these attributes for different detection mechanisms. Now, what is also interesting here is that you see that in the DFT, we have 25 attributes, and in the case of DFDC, we have all 41 attributes, but for DF 1.0, it's only 19 attributes that are present. Okay? So if I want to study a particular attribute, I can pick the database based on these analysis. And then we should also acknowledge the other people, right? We are not the first ones to do this, to work in this direction. There have been people that have been worked before. There have been people who have studied different protection models and different attributes. And in the first one, they only studied the 4 attributes and one data set. In the second one, it was 2 attributes and 3 models, 1 data set. And in this case, we improved the work by having multiple data sets and also multiple annotations. Now comes the next point, right? What is actually causing the problem? Is it the correlation or is the confounding, right? So maybe if some attributes are present, inherently other attributes are also present. So that means there is a relationship between these attributes, right? So how can I separate them to 2 different disjoint sets? So this is a bigger problem. So we could not solve this problem completely. It's an open problem, which I will give an idea in the end. But here, before we understand that, why do I talk about the correlations? So attribute correlations are very strong in certain times. Now, if you look, just ignore the diagonal line, it's a heat map. Now you can see that if somebody has a shiny skin, then it's also likely that the person is black. Is it actually true? Not necessarily, right? So, but we see such kind of correlations between the different attributes. And even worse is that you see the negative contributions. So it says if you have a big lips, then you do not have a pointy nose. Right? Again, there is some inherent correlation, which is telling that, okay, if somebody who has a big lips will not have pointy nose. So if my system is making a decision based on the big lips, then it will make a negative decision based on the pointy nose. Right? Which is again, if you look at the population of the world, there are certain population who might be having pointy nose and certain population who might be having big lips. That's for the sake of the comparison. Let's take people from Africa have big lips, and people from India have point, that means that the system is going to classify them differently for these two populations, which is a problematic scenario, right? And then even the other aspect is that the appearance of mustache and goatee. So some people have different style on their face, facial hair, and they also exhibit a very strong correlation. So if you have a goatee, it's most likely that you have a mustache, which is kind of true, right? You typically have that kind of correlations. And then if you have a square face, then it's likely that you're going to sport a goatee. I don't know how true that is, but you can see that there is a correlation between these attributes. Now, is it a correlation or is it conformal? That we are not able to establish, right? Because we can't really do systematic experiments in this case. So we took up this aspect to study, and then we only focused on some of these algorithms. We said, okay, whatever the database is, it is the database, right? We cannot do anything. We can only go back and collect the database again, but it's a very expensive process. So instead of that, can we try to understand how the algorithms are performed? If I understand if the algorithm is biased for one particular population, maybe I can enforce some measures to correct that course. So to do that correction in the course, first we did was we took this database and we tried to study what happens normally without the attribute being into the picture. What happens typically in the case of deepfake and the deepfake detection. So if you take the original images which are clustered in this dots here, you see that these people are here. And now if I have all these three techniques that we use, four techniques that we discussed yesterday, one is deepfakes and face-to-face, face swap, and neural textures. So all of them are somehow clustered in different regions. So which is kind of good. So if the same person is here, he's also classified as deepfake in this case, and he's also classified as deepfake in this case, this case, this case, and this case. Now comes the problem, right? If I'm going to create a decision boundary, which tells that if I have a nice decision boundary simply like this, then all of these people will be classified into one category, and these people will be classified into another category. And now, although this is deepfake, they are being classified as real. Right? Now you say, okay, maybe that is not a good decision boundary. I invert it, so I do the same thing here. Now you see another problem here. The woman that was classified as real in this case will be classified as fake in the other two scenarios. So this is just a Disney projection. It's nothing but your the one that we saw in the class activation maps where we're looking at the activation. In this case, we are looking at the features. Okay? It's a standard mechanism to visualize the features. Okay, so the idea here is that if I train on one system, it will be probably not good for the other data set. Now, to understand this, what we did was we just simply took the existing data sets with all the annotations, and then we took 30 frames from the first 300 frames by sampling it in 10 frames. So the first frame, 10th frame, 20th frame, and so on. By selecting that sub frames, we had a new data set which could representatively verify with all of the attributes. Now, then comes the problem, right? The other problem is that which model should I verify? Maybe Susanta has one model, maybe Manvi has one model. Which model should I choose? All of these things. So to do that, there is no standard gold, state-of-the-art gold standard. So what we did was we said, okay, let's take 3 random models and let's try to study them. And then based on that, we can derive the conclusions. So we took some frequently used models, which is efficient at B0, exception, and capsule forensic, back in those days, right? So back 3 years ago. And for every single data set, we enforce the standard split of 60% training, 20% validation, 20% testing. And then we looked at, okay, fine, now we can establish the performance, but how do I establish the performance with respect to the error rate? Is it only the accuracy, or should I add something in? So there we divided the error rates into 3 parts. One is the overall error, so combined for deepfake and the real images. And then the fake error itself, which means how many deepfake gets misclassified. And then for the pristine error. Christian error is nothing but how many real images get misclassified.
Sir,
Yeah.
if we take the example of AS1 C++, in that we have multiple deepfake potential techniques.
Yeah.
So can we use like that? We take the frames of deepfake, neural texture, face to face. We take from all these, we get 5,000 images, frames.
Yeah.
And from the original one, we take 20,000 that one, and 20 from the original. Then it will balance data.
Yes. Yes. So the question here is that if I have 5 different generation mechanisms, let's say we have the data sets from deepfake, and then we have neural texture, face swap, and face to face. So if I take 5,000 from each of these category, and then I take 20,000 original, can we consider the data set to be balanced? In terms of numbers, yes, but in terms of variety, they are not balanced, right? So because I have 20,000 of real images, while I have only 5,000 of each of these representation. So the balancing is it's a slightly trickier problem here. So it is better than considering just 20,000 of real and 5,000 of one category than combining them. But then the evaluation mechanism is also different, right? So what are we doing? Then we are doing all sample training. So I'm putting in all the fake samples, all different families of fake samples, and then I have one family of real samples. And then there is also one other evaluation mechanism which is called as leave one out validation, which means you train your algorithm based on ABCs, you leave the D out, and then you verify on D alone. And then you swap it. So then you put D, you put the D, B, and C for training, and then keep A outside, right? So the balancing act is very tricky. So there are some limitations with that. You can't really have equal representations, right, in any case. So the better balance, the better the system is. Okay?
It will affect or not?
It will affect. So I will show you the results later on. Yeah.
So generalizability will also be compromised.
Generalizability will also be compromised. Yeah, generalizability is an ongoing problem, right? Whether you do it balanced or not, it will still be a problem because you do not have all kind of representation. Unseen data is unseen data. You don't know what kind of technique will come tomorrow. Yeah. Okay, so what can we do? We introduce something called as relative performance. The relative performance only measures the ratio. So when we say the ratio between them, what is the error when a person is bald versus what is the error when the person is not bald, right? So you have the error which is for that particular attribution with all the positive annotations, and the error in the same person with negative annotation, right? So for other example, it's like when the person is wearing the glasses, all the people wearing the glasses, the error of that person of all that population with people not wearing the glasses here. It's a ratio, right? So I'm just establishing a ratio between them. Then I can give a relative performance. And then there is also this corrected relative performance, which tells that if I have a data which has all these attributes from this one, from this RP, and then if I have a control data, then I can measure the performance between. So if you look at the formula here itself, it is nothing but a ratio between two aspects, right? It's a ratio of control people minus the data, actual data. So that way I can establish how much it will impact the system if I have this kind of particular data coming into the system. So now, maybe this is a bit fuzzy here, but if you look at this one, so this exactly is what is happening. So what it tells is that if you have a point, your error rates will be minus 150% here, compared to somebody who has a double, let's say somebody who's smiling here. So in that case, the relative performance is approximately 70-80%, and the corrected relative performance is dropping slightly down. Okay. So ideally, what you would want it to be in a clean cluster in this region. So the error rate, relative performance, and the corrected relative performance should be clustered everything here. Right? So, but we do not see such kind of behavior here. So what it also tells is that if your error rate is around, I don't know, for Asian ethnicity, the corrected error rate is around 56%. If you do not correct that error rate, you're going to end up with 57%. You see there is a small difference, right? If you look into the paper, there is a bunch of tables which tells very specifically each error rate, but you get the idea here. Okay? So which means whatever the algorithm that you are creating, if you are not looking into the correction part, then you're going to report the numbers that are not realistic. You might go out to sell your system and tell that my system works 99% accurately, but then if you correct it, maybe it drops down to 94%. Okay. So whenever you're creating the algorithms, it's important that you take into account that the attributes, all the attributes lie in that small area. It should be in that 0% error rate, right? Plus or minus 1 or 2% is okay, but not otherwise. Okay. So what does it really mean to us? If you have real people, so it's a 2 by 2 matrix. Now, if I have a real person's there and the prediction is quite good, so it says, okay, this lady and this lady are predicted as real, but now the same real people are predicted as fake here in these two cases, right? Now, if you look at the other side, this is good because it's a fake image. You see the patch here, and it is classifying it as fake. But for no reason, it is telling that these two people are fake. Now there is inherent bias there, right? So the error rate is coming without, because we are not accounting for all the attributes. And it gets even worse if there are some other ethnicity. Assume that if it was a different scenario, if it was a white person versus a black. So if all the black persons are just classified as fake, and all the white person is classified as real. And vice versa, it could be the other way as well. Okay, so what it does kind of tell us is that there is imbalanced performance due to different aspects. One could be because there is an imbalance in the training data itself, or the way the network is learning the shortcuts. Or the other one is like what kind of training process are we doing? So are we sending all the batches, all the white people first, and then the black people and the brown people and the Caucasian people and the other ethnicity, or are we mixing all these together? So in every single batch, is all the population equally represented? Right? So that way we are trying to balance out the error rates by looking for a better training process. And here, it's also very interesting to note that although this is initial observation that we make, there is a lot of scope for people like you to come up with some new solutions to do some deeper investigations. Okay. So, and then you can collect all new data sets that are and merge all those data sets and then try to understand each of the factors. And there is also this other problem which we often ignore. One of the problems is that where is this data collected from? Like what kind of cameras are being used? Maybe for celebrities, they're using this high quality DSLR cameras, but for other people, maybe they're using some low quality smartphone cameras. Now, where is this bias coming from? Is it coming from the camera itself, or is it coming from the appearance itself? Right. So there is this other approach where you can really make a significant contribution, which is more meaningful for the society as well. And then this was the overall performance, right? So we saw that overall performance is not very good. And now let's look at the fake versus real. And in this case, if you are just taking the real performance, pristine data relative performance, which is on this side, it's a corrected performance. And then if you are taking the deepfake performance, which is true error rates, right? So now what we want is we want something that is in the center again. So if the system is giving 0% error rate on real data, it should also give us 0% error rate on the fake data. But here you see something again very interesting. You see that some of these factors are clustered here, but now the moment you introduce somebody who's wearing a hat, it tells all the time somebody is wearing a hat, the correct performance of this person is around 20%. But now, if the same person is wearing the hat, the chances of making the error on the deep fake is reduced by almost 25%. Right? So it should be ideally it should be balanced, right? If my system is very good, the system should give me 0% for real and also 0% for fake. But we know that in the ideal world, we never achieve 0%. So which means it should be in plus or minus some percent, but the transition is so much different here. Now, in the other extreme case, let's assume people have for their ethnical whatever the background they're coming from, maybe they have a big nose, right? So in the case if they have a big nose, this is something that we cannot do anything about, right? It's appearance. And in that case, you see that the fake error rate is around 45%, but the real error rate drops down to minus 200%. So what does this actually say? It also says that you have some detection modules where some of the real images might be classified as fake, and the fake images can actually be classified as real in differential manner, not equally. Okay. So let's take an example of this one, right? So if you take a problem of this double chin, so in the case of double chin, you see that the prediction of that real person is identified as real person, which is very good. But then the real person is identified as fake in the second case. Okay? In the third case, if you look, the fake person is predicted as fake, which is very good. But in the other case, the fake person is predicted as real person. Now, the commonality here is that the chin, right? The appearance of the chin is making a difference on the algorithm, which is not very good if you want to deploy this. Another example, this is very focused on the ethnicity. So here you see that for the same ethnicity, people of same ethnicity, it's saying that, okay, real person is identified as real, but the real one is identified as fake. In the second case, it's the vice versa. Now, here comes another interesting question, right? So another interesting question is the quality of the image. You see the quality of the image? It is very detailed. So now what is the system making the decision? Is it making the decision based on the quality, or is it making the decision based on the attribute? Okay. Okay, so again, the idea here is that they kind of indicate some varying performance for both real and fake data. Irrespective of method, when I'm saying irrespective of method, all the three methods that we have used, right? It is very similar observations that we make. So what can we question here now? So we can question the model itself. So have we learned a good model, or do we have a good data? Right? So that is a question that again needs to be answered. If we can answer this one, we'll be able to answer the question that the detection models are actually fair. Right? So this is the same thing that you can also do for face recognition. But in the face recognition part, it also has a bigger impact because in most of the Western countries, at least in US and Australia, they have started using the body cams, which makes decisions on the go. So if I'm walking through the street and I find some suspicious activity, then I can arrest the person, right? And now this detection system, which are available on the body cams, when it comes to the reality, they might be very biased, which might lead to a lot of wrong arrest. Okay. Okay, so again, a nice part for many of you to contribute, which actually can make significant difference in the field. And here, the idea is again, remember that there is correlation. We do not know if the appearance of big lips and lipsticks has a correlation, or if it's a confounding fact. So that needs to be studied a bit deeper. And then also the bias effect between the real and the fake images itself. If it is really doing the detection based on attribute, or is it detecting the fake versus real? Okay. And then comes the second part, some suggested directions. So I will just, this was one of the comment that was raised by the reviewer, which is very interesting comment. The reviewer raised the question telling that, are you actually differentiating between the correlation or is it causality? Which we try to understand. How can we do this problem? How can we solve this problem? It's a very difficult problem to solve. So unless you have a controlled data set, because you are working in the university campus, maybe there is an opportunity for you to collect such a data set which can differentiate between those two aspects and then try to establish a model. So a new data set is very much welcome. So if you plan to work on your thesis and you are looking for an interesting problem, this could be a very interesting problem. But just be also very aware of the fact that it's a tedious process, it's a time-consuming process. But they have to collect the data, annotate the data, and then curate it, and then release it for the public. Okay, just as some the bottom line here is that our analysis, whatever we publish in that paper, is best under circumstances. It's in no way the solution to the problem. It's only showing the problem. It's only telling that, okay, there is an existing problem. People can contribute in this direction. Okay, and then there is also this nice work I recently came across. The work is about mitigation strategies, and they make use of generative adversarial network, where they say, okay, I know that the population of white and black is imbalanced. So what can I do? I can use this generative adversarial network to generate more number of samples of black people versus the white people. So in this direction, one of our colleague, Praveen, who is also on the call, he worked on some synthetic ethnicity alteration. So his work is also available on this direction. So where he makes use of GAN to create multiple ethnicities from one single ethnicity. So the idea is that you take a white person and then you try to make him look like how he would be appearing in Asian populations, or how he would be looking in a Caucasian population. So that also helps you to create diversified training data. So this diversified training data can be used for retraining the models. Okay. So these are two approaches. So those of you who are interested in understanding this aspect, you can get in touch with Praveen. I can share his email ID later on. So he works with NIT in SVNIT in Surat. So he's actively working on these areas. Okay. And then at this same time, there is this very old paper from 1951, which talks about what is called as the paradox, which is popularly known as Simpson's paradox. Now, Simpson's paradox talks about the idea that how do you actually make these decision boundaries, right? How do you establish the interaction between the fields? A very old paper, very interesting one. This could be something that is relevant for you if you want to investigate a bit more on this direction. Okay, so now I can start talking about the human aspects. Before I go there, any interesting questions, interesting thoughts?
We can generate synthetic values from GAN. So does it need actually the human generated value? Yes, human collected
Correct. Yeah, very interesting question. So the question here is that if I have a very good GAN model, why do I need to go back and collect the data from people? So it's a very nice question, right? So now if you think about this problem, so you can also think about the idea that whatever I'm going to create synthetically, that will not represent real world. I can simulate the data in maybe let's say in the campus in Jabalpur, but it will not really represent realistic data. So one of the popular mechanisms, at least we have been trying to advocate, is that do your training on synthetic data, test it on synthetic data, but also try to validate it on real data. So only when you validate it on real data, you'll be able to establish what is the performance. Right? So even if you're not able to get like 1 million images, we still recommend that you collect some real images so that you can test how the synthetic data is influencing the real world. Yeah. So, and this is also a popular mechanism used for face recognition. In a couple of the European projects that we were conducting, this was the way to go, because in Europe we cannot really go out and collect millions of images. Right? So that is the idea. So you collect you create the synthetic data set, but then test it on real data set.
Publish the particular data set. Is there a particular number to minimum this number of images to be present to publish the data set, create a data set?
No, there is no gold standard about that. But the only thing that for that reason we use this ROC curves, right? If you look at the ROC curve, it's in the log scale you can establish the trends. It shows you how the graph would go. It gives an estimation of how it will scale up for different populations. Right?
Based on application.
Based on the applications, typically. But if you do the ROC analysis, that's very good, right? Because then you can establish how much the graph will drop at a certain point of time. If you see an abrupt drop in the graph, then you know that okay, it will not scale up for larger population. But if the graph goes very straight, then you know that even though the database increases by log scale, the performance will not be dropping abruptly. That is one. And the second solution that you can do, which we have also been doing recently, is the statistical testing. So you know this classical statistical test, right? Like student t-test, pair t-test, all these tests, right? So they will support you from a different angle. So you have the ROC analysis. In addition to that, you establish, okay, with 95% confidence, what is my system's performance?
Those are the supporting statements.
Those are complementary support techniques. So it's always recommended. The field is moving towards that direction, right? Because we are having the data scarcity, so you cannot collect millions of images. So you report the performance from the metrics part, and then you do a statistical test to validate if the results are trustable. So this is if you look at some of our papers, you'll find all the tests are being done. Good. And then the next part is I'll talk about the other aspects because we started discussing about this yesterday. The idea here is that, okay, I can create the world's best system, but in the end of the day, it's humans that are getting impacted, right? So that means we have to take into account the human aspects as well. So how do we take into human aspects as well? By studying how humans actually perform, both in terms of identifying, detection, or understanding the data set, understanding the performance. If a machine is telling that, well, all the images from Susanta is fake, why should I care about that? Is it actually fake? And then how do I tell Susanta that your images are being rejected continuously? Right? So this is the idea behind this. So I'll give you some representative images, and this can be extended for many of your own works later on. So the idea here is that if I have an image, which is on the left side, which is a normal image, and then I simply introduce some kind of geometrical distortion. And this geometrical distortion can come from your capture process, right? So you hold your camera very close to your eyes, very close to your face, then the face might look a bit bulged. And then if I hold the camera a bit behind, then it might look very thin. So across this manipulation, systems do perform to some extent. But then if I'm a human being sitting and observing all of you passing the airport border, then I should not be rejecting you just because the face doesn't look very similar to that one. Assume that this lady has given the picture on the right side, and she comes and in front of me with that particular face, and then I'll not be able to distinguish between these two people. So we need to establish how these systems actually work for when human is in the loop. So there is this popular term in the machine learning community or the AI community, which is called as human in the loop and human out of the loop. So most of the systems that we interact on a day-to-day basis, whether it's medical imaging or border crossing or other kind of access control applications, there is always some kind of human involved there. Same thing when you enter the gate here, right? So when you enter the gate here, what does the security personnel ask? They ask you for your ID card. What do they look? They look the name, they look at the photo, and they look at you and they say, okay, please go inside. Right? And there is an interaction happening between the human decision making and the automated system, which is your ID card. Okay, let's try to see what happens in this human aspect, right? The idea here is to give you not just the human, not just the machine part is important in AI, but it's also the human part that's important in AI. And this was a work that was done in interdisciplinary manner. So yesterday there was a question, I think, Mami, you asked me this question, what about this interdisciplinary research? So here is a classical example of that. So we have people from human sciences background, we have psychology, people from psychological background, and then we have people from biometric research background, and then we have people from the police department. So all of them have their own individual unique skill set, they have their own competence. So then we brought them all together for this particular work. And the idea here was to study how the algorithms perform. So this graph you remember from yesterday. So I told if I create a good morphed image, so it should be able to attack both subject 1 and subject 2, right? Now this is a similar thing that we see for different kind of attacks. We see that, okay, this attack is not really performing very well. It's very bad, right? This attack is okay, but not the best, but this attack is the best. So I have some systems which can fool the systems. I have some attack mechanism which can fool the systems very well. and some attacks which are very bad for the automated system. They can easily detect those attacks. So if I simply put a threshold on this kind of attacks, I say that if the score is less than 0.4 and 0.4, you check that particularly. As simple as that. Now, what happens if I take those images and give it to the people who are trained, even the low quality images and the high quality, and ask them to do a comparison? So the experiments were done in a very simplistic manner by putting two images on the screen on a simple website and then ask them to tell whether it's real image or whether it's attack image. And in another case, what we did was we showed them just one image and then asked them to say if it was real image or a fake image. And the idea here was to understand what happens in the human brain when they make a decision. And these are all the people that are very well trained. So if you look at the number of people that we had, so we had like 150 people who issue passports and visas, and there were 30 people who actually sit in the borders when it cross the borders. And there were also the ID experts, which are very well trained in identifying if the ID card is real or fake. So we brought all of them together. We launched like a large scale experiment. This was done by one of our master student from Sri Lanka. She did a brilliant work together with our current PhD student who is here. So both of them did these experiments in a very nice and controlled manner, and they established something very interesting here. So what they found out is that if they give two images and ask people to tell if it's a real or the fake image, then the first category of people, the people that are sitting in the border guards, in the border control, their performance varies from 87% to all the way to 40%. So what does this mean? This means if a border guard is sitting and checking the attack images that is being inserted into the passport, so it is likely that 40% of the times somebody gets away. Or in a population context, 40 people who are trying to enter the country without the valid documents might get away, which is a big serious security risk, right? So now all of these attacks are again generally conducted using this generative AI techniques that we have been studying for the last couple of days. We have been reading about a couple of days. And the trend is very bad, right? So if you look at the same person, if the ID experts are sitting, some of them even have less than 20% accuracy. So if we have a very unfortunate situation, we are sitting here, this person is the one that is verifying the document, and then 80% of the people who should not be in a particular place can get access to that, which is bad for the security, right? It becomes even worse when you have only one image to make a decision on. If I have one image and then I tell them, okay, is it a real image or it's a fake image? Their accuracy, the best accuracy is only what, 76%. And the same one, if I have a reference image, then I have an accuracy of 87 or 97. So when it is single image, then the accuracy drops. So again, there is a number of aspects that are not studied here, which might be very interesting for your research works. The idea is that if a particular person is making very good decision, like let's say this one, right? This case number 6 is very interesting. You see, they almost have 100% accuracy. So what is it making that they are very good at this detection? So then comes the idea of understanding the human psychology, the brain processing, and then the decision-making ability. So at this point of time, we did not do man-machine interaction, right? So we did not give them the decision from the machine itself. So that is still understudied aspect. So if you are planning to do some experiments, you can consider including that into the pipeline. So you give a decision to the human, and you tell the machine is telling you that this is a fake image with 97% confidence. What do you think? Maybe we'll find out some new observations from this kind of studies. Okay, and then let's think about the other aspect, right? So we only saw what is known as the morphing attacks yesterday, and we saw what is known as deepfake attacks. But what happens to the other kind of attacks? So it is very interesting here. So if you have the people that have just simply beautified the image. And this is a very common thing in the Asian part, right? So whenever I'm going to give my picture to the passport, I always do some kind of editing so that my passport image looks very well. And even worse is that in the Asian countries, especially in the Korea and other places, there is this surgical manipulation. So people do not really like their appearance. Maybe they want to improve the facial appearance, and they go and pay huge amounts of money to get this surgical facial plastic surgery done. So all these have a negative impact on the human observers. There was even a very interesting case recently. There was a lady who was traveling from China to Korea with a passport, and she got this surgery done, and she could not enter the country back because none of the systems were matching her face with the altered face image. Right now, which is a very similar thing with the humans as well. So here you see, in fact, the attacks, the morphing attacks, is not the biggest threat in this case. You see, the attacks were having an accuracy, the error rate of 40%, but the beautification had an error rate of 85%. Even worse is that the images that were not really manipulated, the real images, they also had a very high accuracy, a high false detection of 85%. That means humans are also making very wrong decisions here. Not just algorithms as we saw in the previous case, but also the humans here. So what did we do in this case was that we identified a bunch of super recognizers. I don't know how many of you know about super recognizers. Is there anybody who has heard this term before? So super recognizers are typically these people who have this extreme capability of identifying people. So if they see you today, and if they see you after a couple of days again, they will identify you. This is the person that I know, right? And this can be a lot of different abilities. So it could be inherent ability, which means that they're born with such ability, or it can be trained over the period of time. Right? Yeah. Typically, the the experts that we train in the police department, they are trained every single year so that they become better. So they have this constant training programs. So what we wanted to identify in this case is that how much is what is the role of this training effect? So if they are trained every single year, are they becoming better, or are they just being better because they have this natural ability? And the second one, super recognizers are typically in the case of identification of people, right? So which means they only can say, okay, this is Manvi, this is Santa, but they're not good at saying fake or real. So we wanted to also check if somebody has the ability of this extreme ability of differentiating between people, are they also good in differentiating fake and the real ones? So this was the study where we had to really take the help of people from different fields, like people who understood psychology, people who understood social sciences, and we brought the whole team together. And in this case, the very criteria to determine if somebody was super recognizer, let's say if I'm interested in finding out if Arif is a super recognizer, then what I would do is I would ask him to go take this test. There is the CFMT test, which is based on a couple of images, and then you have to verify each of the image, and then you get a score. And then there is also alternative test called as Glasgow face matching test, and then there is the Kent face matching test. Then there is also this other face recognition test, which are all some variants of the face recognition capability. So in this team, we had this original authors of this particular test, Robertson from UK. That group also helped us with running these tests. And when they ran this test, there was a strict criteria that was enforced. We said, okay, whatever the test you're getting, the test should be at least of certain score. And in this case, we said that if your score is more than 96, then we consider you for the test, for this kind of experiments. If it was less, then we would just eliminate them. Because then we did not want to derive the conclusion based on somebody who's not really good at this kind of test. So with that test, you can see that we had a range of around 91 to 102. So then it was 96 point was the mean. And then for the GFMT, it was the average range was 38 to 40, and the average score was 39.7. And you can see that it was a very strict criteria that was taken into account to tell if Arif was super recognizer or not. And then we also introduce some other people, right, who are control group. Control group could be you and me, who do not necessarily have that capability, but we are still okay in distinguishing between peoples. So we took these people and then we showed them a bunch of images, and this bunch of images were diverse images again. So we took some face swab that we saw on Monday, and then we took morphed images that we saw yesterday, and then we took retouching images, which is just beautification, right? So we take that person and then we beautify that person by making the eyebrow finer, making the eyelashes look better, and skin color look better, and so on. So what we did was that we showed these images to all these people, and then when we showed these images, there was also the other scale that was introduced. So the UI looked something like this. So we had one image on the left side, which we called as trusted live image, which is nothing but I trust that image. It is not manipulated, it's a real image. And on the right side, we are flashing images that we did not know. It could be morphed image, it could be beautified image, it could be face swapped image, whatever the image was. And then we asked them to tell whether it's bona fide or manipulated. Manipulated in the sense it could be any of them, right? And then, since these are all super recognizers, we also wanted to ask them, what is your confidence in this? Which is exactly the same thing we ask the machines, right? So the machines give you a score, it tells that this image is manipulated, and then it gives you a confidence interval. It tells that I'm 90% sure that this image is manipulated because it's a probability score that you're getting. So we introduced the Likert scale here. And in the Likert scale, we had these two different sets, which is called as DFMD1, which is downstairs face matching test. And then we had the face manipulation detection test. And there was a subset, which was called as 2. In the, again, since the experiment was conducted in a very large scale, we invited around 787 participants. And in that 787 participants, we only chose 89 people who really had this control test done in all the 3 tests. So 4 tests we had. So from the 4 tests, at least they should have scored at least 89. So they should have scored more than a particular threshold in all 3 tests. And then we had to balance it out, right? So we also invited all the other people who were not really acing this test. So we had this bunch of people. So in the first case, 50% of the images were manipulated. So any number of trial that we were doing, one was real versus the fake, and there were 50% of them real versus fake, 50% of them were real versus fake. And then one of the officers that we collaborate with raised another concern, telling that in real life we do not see so much of manipulated images. We probably see only 20% of manipulated images. So to take into account that one, so we did the second test where 75% was real images and only 25% was manipulated, which is common thing, right? So if you go to a Jabalpur airport, you will likely see real people all the time. Maybe one in 20 instances, there will be one person who's trying to fool the system. Okay, so we try to do that analysis here. And then the question was about how do we select the data set, right? There was a question about this. You asked me this. So in this case, this is quite easy. There is something called as G-power analysis, which tells that if you put all of your numbers into that, what kind of experiment you are doing, it will tell you exactly how many participants you need. And it also tells that what is your confidence level. So if you want the experiment observations, the observations from the experiments to be with 95% confidence, you set the alpha level to 0.05. And then it tells you that it's only you only need 51 participants, not more than. But now we have more people, right? So we can validate statistically in a nicer manner. Okay, and then this is not very interesting, but here you see I'll share the slides, and you can see how the trials were done for your own experiments later on. But what is interesting in this case is that you have this DFMD1, there was high accuracy when it was 50% manipulated images. There were very few false alarms. which means they were quite good, right? So the super recognizers were quite good. Now, in the DFMD2, very similar trends were noted with even with lower prevalence of manipulated images. So even if it was 25%, they were still able to do good classification. So just look at the graphs here. So if you look at that, we are putting each of them independently, and you can see that the accuracy for super recognizers is 72%. And then for the control group, who did not have this extreme ability, they were still doing good. They were doing 63%. But what is interesting here is that although there is 63%, super recognizers are really not performing at selling. So they have some ability, but not the best of their ability, right? So there is some gap here, which we can try to resolve. And here you see that the controls have some varying performance. If you read the paper, you get all these full details. But I just want to show you the trends here. And the trends clearly show that control groups are far below the super recognizers. They're overlapping, but the average is much higher for super recognizers. That tells us that there is something in the training mechanism that we are doing which helps them to become better. So what does this mean? This also means that is their ability equally across all different kind of attacks? If you look very closely, you see that their ability is very good for morphing attack detection, and their ability is very bad for retouchings, right? So the accuracy dropped from 73 to 72% here. So the idea here is to just tell you that the cognition part is still understudied. So for those of you who are still looking for a very nice problem to study, so here is a very good interdisciplinary problem. You can bring in people from neuroscience, you can bring in people from the police authorities, and then try to run these experiments to understand what really happens in the human part. Okay, and then we also wanted to study what happens with the order of experiments, in the sense, first they get to see 50% fake images, and then we show them the images which are far lesser, so they become better. And we clearly say that here there is a change in the order. So if the people do first 50% and then 25%, or if they do first 25% and then do the 50%, the accuracy also changes, which kind of indicates the more number of images that you're showing them, the better they become, which is what we call as volume training in pedagogy, right? So if I'm giving you 100 mathematics problems to solve every day, just by solving the problems every single day 100 times, you become better at math. What is typically is the volume training, right? You're not doing anything special, but you're just making them to understand the problem by giving them n number of examples. This also tells us that there is some hope for the future, in the sense that if you really are struggling with the systems, then they can be made better by training the people over and over again. Right? Now, why is this also important for us? So tomorrow, when we come to the point where we have these medical images and we want the doctors to be making automated decision, and if we realize that the doctors are not good at identifying this pathology or the tumors based on the AI system, you can make the dedicated training programs and train them so that they become better at using these systems. Here's an idea. So although it's only for the face recognition here, but it can be applied for a lot of other aspects. And the same thing for media consumption, right? How do you train people to understand if the media is fake or if the media is real? The misinformation spread. So how to train them to check the facts. So just by giving them a lot of examples, you can make them better at understanding if the media is real or if it's fake. Okay? This is also a very understudied topic. So if you are interested in looking at this aspect, it could be very interesting if you run these kind of experiments and try to understand what happens when people consume fake media. Now, when I'm saying media, it could be an image together with a news article, right? This we have seen in the past couple of years. Okay, and then just to kind of give an indication, there are a lot of different details in the paper that you can read later on, but you see that the accuracy of a particular person, the control and the score, for each image is varying. So we do not see a trend here, right? We see that some images are very easy, some images are very difficult. So the one on this part, the image number one has very low accuracy, and the image number 60 has very high accuracy. So it also tells that as people tend to see more images, they become better at identifying the fake images. Okay, and then there is also this other aspect that we did not really study, which could be interesting for you all to study, is the ethnicity. I showed in the previous case what happens with the algorithms. The black people are discriminated from the white people, and the same thing can happen with the humans as well. So there is this popular term which is called as other race effect. For those of you who study this, at least have taken some subjects in psychology or understood some concepts of psychology, you know this aspect called as other race effect, which means that me coming from a particular race, what am I used to? Me as an Indian, if I'm looking at all the Indian people, I'll be able to distinguish each of your faces, right? But if I'm given a bunch of images from China, maybe I'm not very good at that. And now imagine the other scenario where I'm growing up in China. So on an everyday basis, I see Chinese. So I'm able to distinguish all the Chinese. But if I come to India after, I don't know, 30, 40 years, I'll not be able to distinguish each of the face image from India because I'm used to looking at the Chinese face. Right? So this is typically called as the other race effect, and this is very applicable in this field. And not only in this field, but also in the machine learning community, right? If you're training algorithm on Chinese people, it will not work very well for the Indian. Okay, so this goes hand in hand with humans and the machines. Okay, so then I'll not bore you with this part, but you get the whole idea that there is this the detection rate varies depending on the manipulation type. Some morphing images are very challenging, while some of the easiest to detect are face swapping. But on an average, all the super recognizers, they have some ability, which makes them also good at this kind of attack detection. So if you, the larger implication, let's say, one of the other implication is also that if you are going to, let's assume tomorrow you're going to create a company, and this company is specializing in detecting fake versus real. So this could be a test that you can run for the employment itself, right? So you can ask people to take this test, and then if they qualify the test, then you can ask them to be joining your team. Right? It becomes like an entrance mechanism for your employment. At the same time, not just the entrance mechanism, but it could also be a mechanism where you can identify, okay, you know what, Manvi is struggling with this task, but Arif is performing very well. So how can I train Manvi to become like Arif? Right? You can also design dedicated training programs for every kind of population that you have. Okay, and then of course this is not a universal observation, right? The universal observation because individuals also vary. So you have people who come from a certain background, they might be performing better, they might become better with the training, but then there are some other people who might not become better at all. Right? So what is the other implication is that you can take those people and then place them in a different line of work. So if I know that the border guard is leaving 80% of the fake images inside, so then maybe he's not very fit to be in that job, but maybe he has better ability in, let's say, in managing the back office. So there is also this use case of employment role changes. Okay, okay then for those of you who are also interested, there are some other open areas which are under study, and these open areas are like, for instance, where do I look into an image when I'm making a decision? Am I looking into the eye region or am I looking into the hair region? Right? So this also becomes very interesting. Now, by doing this, what can I achieve? I can now use these attention maps to go back to your training transformers, right? Or training your deep learning networks where the attention is driven by human observation. I find out where people are looking at the particular image, and I know that, okay, Arif is very good at this task, and I identify where Arif is always looking at the image, and then that becomes an attention. And if I do it in large scale, Then I can have an average attention map, which is good for positive additions. And I can also create attention maps which are bad for the decision making, which I can use it as negative attention maps. Okay, so you get the idea how everything is getting connected back here. Okay, so that is the other aspect. And now maybe I can pause a bit here and ask if there are any questions before I take one last aspect, because if you're going to create the new systems, there is also another aspect that you need to study. No questions?
Split of the data set, that's 60-20 is standard one.
60-20-20 is not really standard, but it depends on how big data set you have, right? If you have, if you read the book on machine learning by hands-on machine learning by Aurelian Gera, he talks about this aspect. It doesn't matter really about what is the split, it matters about how big is your data set. If you have 10 million data set, even if you use 50% for training, it's already 5 million, right? As compared to having a data set of 1000, and even if you have 1000 data set, if you take 90% for training, what are we talking about? 900 images. So that means that training set is very, very big. Okay? So you have to always scale it up with the number of images that are available. Okay, so good. So if I convinced you with some upcoming domains in this area, I'll also talk a bit about the last aspect here, so that we can wind up the discussions for today. The other aspect that I've been talking about is that the capture subsystem in the first part is very beautiful. So that is where you take the presentation attacks. And that is a place where you also need to estimate if the image is good to give a passport, right? So if I put an image which is quite bad into the system, that could make the image, the whole database corrupted. Then my accuracy will be very low. So most likely I'm going to reject that person over and again. Right? So the very first aspect that we need to do is we need to estimate what is the quality. If the quality is not good, I can ask the person to capture image again and then estimate the quality. If I'm convinced that the quality is good enough, then I can put it back into the data set. Which is the same thing that you do when you submit your assignment, right? You write an assignment and then you say, okay, I'm satisfied with this assignment, and then you submit to the system. If you're not satisfied, you rework on assessment, which is a very similar case here. So we do not worry about this part. So we simply say that, okay, this part is fine. And now we focus on the quality aspect. And here comes a number of different reasons why we should talk about this. So the international standards recommend you that the face should be in a particular manner. There should not be smiling expression. There should not be gaze. There should not be the subject shouldn't be too close, because we saw in the previous case, if you have the radial distortion because the face is too close, then it will impact the accuracy both for humans and machines. So what do we do? The two things that actually are unsolved are the subjects really need actionable feedback. Right? I can't simply tell that the data is bad, recapture the data, but rather I should be able to tell them why the data is bad. Right? So that is the idea here. So if somebody is smiling like this, I should tell, please do not smile, give a neutral pose. So that is what we call as actionable feedback. So the actionable feedback is still a very open research problem that can be solved if you're all interested in contributing towards that. And then we need to have this standards that we need to respect, right? So in standards, there are some objective metrics. What does the objective metric say? It says if I capture an image, the distance between the eyes should be somewhere in a range of 125 pixels. I think in the old one, it was minimum of 90 pixels, and it could be plus infinity, it could be as big as that, as big as you want, and then you will resize the whole image. And then you also need to have some other metrics, right? For instance, you will tell the eye position should be in the same line. Why do we need to tell that the eye position should be in the same line? If the eye positions are not in the same line, that means the face is tilted. Right? So we establish this metric. And then there should be a ratio between face and the whole body. If I'm taking a picture and my face is only this much, my whole picture is this big, that means I'm capturing the whole body, not necessarily the face. Okay, so all these metrics are very standard, and these metrics are also what is popularly used for your passports. Which means if you are carrying your passport and if you're trying to use it in any other country, the image standards will be very similar everywhere. Okay. So just to touch upon the different kind of quality aspects here, what we want is we want something that is compliant image, and we want something that is uncompliant image to be rejected, non-compliant image to be rejected. For instance, you have two images there. The compliant image is okay, and the other one is having extreme exposure. So we need to reject that image. So to do that, there are a number of proposals that have come from different people. People have said that we should use unified quality score. People have said that we should use illumination uniformity, how much does the focus change, and all these aspects. And each of them can be having an impact on face recognition. So from this one, you can already see that this is a draft table, right? So which means that tomorrow, if you come up with a very brilliant idea, you can always propose that idea to say that, okay, this is a good quality metric, I can use it further. And then here, if you look at the quality components, then there are two different components. One is overall image, and the second one is component quality, which means how good is the illumination, how bad is the focus, how bad is the blur. And again, if you look very closely into that table, you also see two other aspects. So what is the two other aspects? The things that are related to the capture, which means they are scenario based, right? So if I'm capturing the image in this room, there is a certain setting that I cannot change. I cannot control those aspects unless somebody changes those things. And then there is something that is subject related. So subject related is that what if I'm smiling? What if I'm having a gaze? So that is something related to me. And then there is something related to capture. Okay. I think this is the first time you are seeing this graph. I just should let you know what this graph is. So you have understood the graph of FR versus FRR, the DT curve. So in this case, what we are trying to do is that we are trying to reject a certain amount of images, and then we are trying to measure vertical performance. So the idea here is that you reject 10% of the bad quality, 20% of the bad quality, 30% of the bad quality. So every time I'm reducing the bad quality images, the false non-match rate should go down. Right? So if I have a bad quality, that will result in a false non-match rate. And if I simply eliminate it from the database, so then my performance should become better and better. So there's a very nice survey that has been written by some of our colleagues, and that gives a complete picture of this. And the code for that FNMR generation is also available, which I'll show in some time, where you can just go and just download it. And here you see how the unified quality score varies. See, the image is quite bad, and it's getting a score of 0.35. And this image is quite bad, it gets a score of 0.7. So which means unified quality score, which we are going to use, the ones that are derived from those works there, some arc face, mark face, then face QNet and so on, they can estimate the quality as well. So how do they estimate the quality? By measuring the strength of your embeddings. Right? So whatever the embeddings that you're getting, you can measure the strength of that, and you can estimate this quality. So there are this unified quality. And then there is also the second part, which is capture related. Now here you see that underexposure, unnatural color, occluded face, and so on. So all of them will have very bad influence on the face recognition. So you want to delete them. And then you also have the second part, which is subject related, which is smile and other aspects. Okay, I'm not go much into detail, but I also wanted to just remind you yesterday that we saw about this fingerprint. We spoke about NFIQ, which is the fingerprint image quality metric, and you can have a similar mechanism there as well. So you use multiple systems to establish the quality. Only when you are satisfied with the quality, then you go towards the recognition factor. Okay, so we are right now in this NFIQ 2.0, but as I told, there is a call for contributions for NFIQ3. So if you are interested in that, try to take a look at that, and then you can make significant contributions for fingerprint recognition in the quality estimation, both for regular fingerprints, also for the latent fingerprints. Okay, I'm not motivate you further here, but you see that if you let people to capture their images, they probably will capture a selfie image in all unconstrained situations. Now imagine you are running a bank and then you want to verify this person with this kind of lighting here. You'll not be able to tell if it is actually the same person or not. So the moment you are not able to identify that person, then maybe your banking transactions will go wrong, eventually which will lead to your loss, right? Okay, so I just want to highlight some work that was done by Praveen when he was with NTNU. So what he did was he took bunch of this quality scores like brightness, contrast, defocus, and everything. And all these things he studied very individually. And you see that ideally what we want is that we want the graph to go like sharp like this, right? It has to go diagonally like that, because if I'm discarding all the bad samples, then the performance, the FNMR should be 0. Yeah, that makes sense. All bad quality goes, that means my whole system should become better. So he studied a number of different components. And then what we also wanted to do was that, can we combine these two individual metrics to one single metric? So I have one unified quality. So I have all the independent components that are measured. From that, can I derive one final quality metric? So he did this in a very nice manner. So what he did was he took number of feature vector, all the big tables that I showed, and from that he created ground truth data set, which said, is it high quality, is it low quality? And from that he trained a classifier simply by putting them as a feature vector, and then he predicted the final unified quality score. And by measuring that, he could show how the system is performing better or bad. So again, the goal is to go to that yellow region, right? The small yellow region. And then he took number of different combinations. He took 3 different data sets, which is LFW, labeled faces in the wild, and then XQLFW, which is a cross-quality LFW, and then color ferret, which is another database. And then he experimented with number of face recognition system and with different classifiers. And here you see some interesting results. So some of the quality metrics, for instance, brightness was going higher up, right? And then the sharpness, it had an impact like this. So what we want is that we want the system to come towards like this. So since each of them were performing very differently, so you try to estimate them using one classifier that was shown in the previous slide. And here you also see that the characteristics are changing for different data sets. So in the cross-quality data set and the LFW data set, the performance is different as compared to color ferret data set. Now, somebody asked me the question, you asked me the question about the synthetic data, right? So the problem here is that if you are training your system completely on synthetic data set, you will not be able to get the performance on color ferret. So color ferret is like really a very old data set which has different characteristics because different kind of cameras were used back in the days. Okay, so I'll not bore you with this problem here, but you see some interesting observations from his work. You see that for some of them, the error rate actually increases. For some of them, the error rate decreases. So there is no clear correlation between them, which opens up a new avenue for you all to go back to this idea of trying to make the systems much better. Okay? So if you are interested in exploring this direction, I strongly recommend you to get in touch with Praveen. He's with the SK19 in Surat, in Gujarat. So he still actively works on these aspects. Okay, and then these are some additional observations that you can take a look at it when I give the slides, but you get the general idea, right? The systems are very varying with respect to different quality metrics. And then there is also the other aspect. How do I explain people that what is performing better, what is performing bad? For instance, defocus, for instance, here has the highest impact. And there I see that it has a positive impact. it also can have some negative. So now comes the actionable feedback part and the explainable feedback part. So if I can derive from some observations from this, I can tell that, okay, I think I cannot accept your image because your image is too bright. Right? So then I can tell that, okay, adjust your lighting settings. Or I can tell them, okay, you are wearing your glasses, remove your glasses and give the picture. Okay, so this is a very open field that is still not solved. But then he also did some other analysis where he established that we do not really have to worry about all the 27 attributes, but even with 7 important features, you can show that the trends are very similar. So this is by using all 27 features, right? So you see the graph that goes down, and then here he took top 7 features, 1, 2, 3, 4, 5, 6, 7, and then he could get very similar performance in that. So why is this important? If you are considering to implement a system which is low cost device, and then you do not necessarily have the bandwidth of processing all the features. So maybe you can do such an analysis and pick only those top features which can be used in your system. Okay, this is again a very open domain. Very few contributions are coming in this domain. So this could also be something interesting if you are looking into new problems. Okay, I think I can keep on talking for other aspects if you want to, but I think I have been talking for the last 5-6 days. So I think it's time for me to say thank you for attending all the sessions. And then it was a pleasure to be here for all the last couple of days. I enjoyed the interactions. I've spoken to many of you, many interesting ideas. I hope some of you will be able to pick up the topics and then work for your own master's, PhDs, or your bachelor thesis. And as I told, if you're interested in some topics to work with us or with Praveen or with anybody else, please contact us. I'll be able to at least put you in touch with the right people. Right. That being said, I think I should thank you here. And then I think we have evaluation and summary. Okay. All right. So then, thank you. So then we can stop the recording here, and then I can take some questions if you have any.